Hey, astronomy students, let's talk ellipses. Ellipses are the shape of the orbit of all the planets, pretty much everything in the galaxy. They orbit things in ellipses. Everything in the universe orbit in ellipses. Kepler discovered this. His first law, Kepler's first law, says that the planets go around the sun. The sun is at one focus. There's two focus points, and the sun's at one focus, and the Earth goes in ellipse, and the planets go in ellipses around the sun. Okay, so that's his first law. So the planets orbit ellipses with the sun at one focus. So you got to know about ellipses, understand gravity and astronomy. So here's the idea. I'm going to draw an ellipse, and this is not a real ellipse. Real ellipses have a precise mathematical shape, and basically they are, if you take the distance from the two focus points, you basically put two dots like that, those are called the focus points, then the distance to every point on this circle, you take those, you add this distance, and you add that distance, it's always the same. So d1 plus d2 is always the same thing. So the sum of those two things is always the same. So if I go to maybe this point over here, this one's close, that one's far, but this distance and that distance, you add those together and they're always going to be the same. I just drew this randomly, so it's probably not going to work that way. Now the easy way to do this is to get a loop of string and attach them around points like this. And then one part of the string is going to be across the middle, and then the other loop of this part of the string is this one and that one, and it will always be the same. Again, these are called the focus points. Focus points, or foci. F-O-C-I-I is plural. I didn't make it up. Focus points, there's two of them. The sun is at one of them, so let's get a nice sun here. So at least the way it works around here, the sun is at one of them, and then the Earth goes in a nice ellipse around the sun. Here we go around the sun. Nothing's at the other focus point, it's just an empty mathematical point in space. Okay, so whatever is being orbited is here, and then the thing goes and orbits around it. For us, like for the moon, we are at one of the focus points, and the moon goes around us. This is a very oblong ellipse. The Earth or ellipse isn't practically a circle. A circle is an ellipse. A circle is kind of a, I don't know, perfect ellipse, but it's an ultimate ellipse, and so we'll talk about that. Yes, so that's the idea. So now first, how to draw an ellipse on your astrology project, ellipse project. You're supposed to draw an ellipse. So here's what you do. You get like two push pins or something, and you stick them in a piece of cardboard like I did here, and be careful because I had them to kind of poke out on the other side, so that way it holds the pins. And then I got a piece of string, and you could use, don't use a rubber band unless you don't pull it tight, because it's got to be a set distance. And then you get a pin. This is really cool, and you pull. Oh, by the way, these are the two focus points. So you can make them close together, you can make them far apart, but the string's got to fit around them. Then you pull the string tight like that, and now this distance and that distance is always the same because it's a loop of string, and then this one here just stays there. So this is the precise definition of ellipse. Those two distances add to the same thing. So one of them gets short, the other one gets long. And as I pull it around, keeping it, oops, I didn't keep it tight there. It's hard to do this in front of you guys. Okay, here we go. Is I kind of try to keep it kind of tight, push it against the paper, keep it tight, and there is my ellipse. Pretty cool. And that is the precise definition of an ellipse, at least as precisely as I can make it with my string and everything. Okay, so on the project, you're supposed to make one like this. Use whatever materials you have, do it on a separate sheet of paper, and then what you do is you find out, you mathematically determine how elliptical it is, and I'll show you how to do that. Okay, so basically, if you have both focus points in the same place, it's a circle, right? If I put both of these in the same place, that's basically like I have one of them, and if I just have one and I pull it around, it's a circle. The length of the string, double or half the length of the string, it's looped, I don't know, is the radius, right? So a circle is an ellipse. It's like the ultimate ellipse. And the further apart I get these, the more I'll make another one. I'm going to put these further apart so my string is almost straight between them. Then I have a more elliptical ellipse, but that's not what they call it. They actually call it eccentric. And if I were to change the world, one thing I would do is change that word. It should be called the ellipticity of an ellipse, should be how elliptical it is. But instead they call it the eccentricity. And I don't know why, but anyway, so now I have the same loop of the string, same 2 points, but well, no, I don't have the same 2 points, different focus points. I put them further apart, and check out this ellipse. Okay, it's going to be long and skinny. See that? So this is kind of a more stretched out ellipse. The further away I put these points, the more skinny it's going to get because the string doesn't have as much remove. Makes sense. And so there's a number called the eccentricity, which tells you how elliptical it is, how stretched out it is. A 0 is a circle, and if you pull them out all the way tight, practically a line is close to a 1. Okay, so the more like a line it is, the more like a 1 it is. So it goes between 0 and 1, the eccentricity, and I'll show you how to calculate that on the board. And by the way, an ellipse is oval shaped, but ovals aren't actually, cannot be ellipses. I mean, you could call an ellipse an oval, but an oval is not necessarily an ellipse. So for instance, ovals don't really have precise mathematical definitions. It's just like a squished circle. So it's not really a precise mathematical thing. Well, ellipses are very precise mathematically. Plus, ovals can be like eggs. Eggs supposedly can count as ovals. So an oval could have a, boy, that's really bad. But an oval can have a skinny side and a fat side, and it's not a precise mathematical shape. So planets don't go in ovals. They go in ellipses, okay? So just keep that in mind. Okay, now let's calculate this eccentricity thing. So here's an ellipse. My approximation, let's say those are the 2 focus points. So they give letters to different things that you need to understand. So I'm going to make those nice and big and fat. So those are 2 focus points, and then this is like the center, right? In between the 2 focus points is the center. Like if it was a circle, that'd be the center of the circle. All right, so they call from the center to the outside. Okay, from the center to the outside, that's like the radius of it, right? That's the big radius. They call that the axis because it's not really a radius like a circle. It only has one, so they call it the axis. And that is half. The full axis is this, right? So this is half of the big axis, and semi means half. So they call that the semi-major, because major means big. Semi-major axis. That's this line right here, okay? Half of the big axis. Makes sense. And they generally give out the letter A. Then they give the letter B. I'll make this in green. This way. That's the small axis, right? If it's a circle, they'd be the same. And that's the semi, they call this B. So this is B. And B is the half of the minor, the smaller axis. Okay, so the semi-major axis, the semi-minor axis. That's how, and if you have those 2 things, you know what an ellipse, you know what kind of ellipse it is. Let me label this one A here. So this is A. Now you got to know the center. When you guys made an ellipse for this, which hopefully you're going to make soon, you're going to know the 2 focus points. What you got to do is measure that distance and take half of it to find the center. Okay, you're going to have to use a ruler. Now, to find the eccentricity, which tells you how elliptical it is. Remember, a circle is 0 because all these things are in the same place, right, for a circle. But to find the eccentricity, what you do is you take the distance from here to here, and they give that the letter C, which makes sense, from the center to a focus point, to 1 focus point. Obviously, a circle, that distance is 0. Then the eccentricity, which is nice, you can generally call the letter E, is just C divided by A. Okay, so the smaller that distance and the bigger that distance, the smaller the eccentricity is going to be. Okay, so E is equal to C divided by A. That is how you find the eccentricity of an ellipse. If you know the focus points, right? So here we know the focus points. So it's always a small number divided by the big number. So if A is, let me see how this makes sense. If C is really big If C is practically A, that means it's a very elliptical ellipse, a very eccentric ellipse, and this gets to be 1. If C is 0, which means everything's on top of here, it's a circle, which is 0. Okay, so always between 0 and 1. Okay, so E is greater than or equal to 0, that's a circle, and less than 1. Can't get to 1, because then it'd be perfectly straight line, but it can get to the like 0.99. So this is a circle, and this is like a line practically, where it just kind of like the orbits back and forth, back and forth. All right, now what if you don't know where the focus points are? Like if I just give you an ellipse to say measure the eccentricity of, you don't know where the focus points are. Well, then there's another formula, and that's one thing you're also going to have to do, and that is, and we don't need to know. I don't even know where this came from. Some smart person figured it out. It's square root of a squared minus b squared divided by a. So you don't need to know where the focus points are to get A and B. You just got to know where the center is. And the center is easy. You take the widest part and divide it in 2. Find half of the widest part. So that's what A is. And B is just the other way. This is half of the narrowest part. And then you just square this number. So if it was 2, that'd be 4. Square this number, subtract them, divide by A. And you can get it that way too. And so you can just measure those with a ruler and you can get pretty accurate to find the eccentricity. On most planets, the eccentricity is pretty darn close to 0. If you looked at the Earth's orbit, you'd think it was a circle. It's practically a circle, just slightly off from a circle. And a circle is a perfectly good orbit. It mathematically can be an orbit, but Kepler found they all go in ellipses, and that's because if it's a circle, if you go around in a circle, okay, perfect circle, here's the sun, and here's the Earth going around in a nice circle. If anything slows us down, we hit a grain of dust, anything slows us down from the speed that you're orbiting in, so you're orbiting along this way in some speed, then that's it, and we're going to spiral into the sun. So a circle is not a stable orbit. It's right on the edge. If anything happens to our speed, that's it, we're spiraling into the sun. Well, if you're in an elliptical orbit, if you slow down, you just go a little bit less than an ellipse, a little bit more circular. It gives you some leeway there, just in case something bad happens and you hit a bunch of asteroids or something. You know, you have some room to spare. If the bigger the ellipse, the better as far as it's safe. However, if too big of an ellipse and you get really close to the sun and really far from the sun, and then you get really hot and then really cold. So like for instance, Halley's Comet takes 75 years to go around the sun, and it is a very elliptical orbit. So if here's the focus, here's the sun, it gets close and then goes really far, and there's a picture of it in the book. This is Halley's Comet. It takes 75 years, gets really close, and then gets really far. So it gets really hot here and gets really cold here. If we did that, we'd be in trouble, right? It's kind of nice that we're practically a circle. We range from about 91 million miles to about 95 million miles. The average is 93, and it turns out that that is the average distance. The average distance turns out to be the semi-major axis, average distance, and for the Earth, right, it's about 93 million miles. But it ranges when we're close to the sun. It gets about to be, not exactly, but about 91 million miles, and as far as 95. So I'm going to exaggerate this because it's practically a circle, but that's not very exciting. So I'm going to make it more of an ellipse so we can see what happens. So here's the ellipse. Here's the sun at one focus. Again, this is not to scale. The Earth, it's practically a circle, but we're going to pretend it's not so we can put some numbers on it. Okay, when we are closest, right, that's about 91 million miles, not 93. When we're furthest, it's about 95 million miles. So there's a 4 million mile difference between those two. Yeah, that's right. And this place has a name. It's close to the sun. The sun is Helios, or Sol, or sun, right? A bunch of different names, but whatever. They use Helios a lot in astronomy. So close to, I think in Greek or something, is Para. So Para, the sun. This is called Perihelion. Perihelion. I'm going to go on top of my ellipse. Perihelion. That's this point right here. And it happens about January 4th every year. You know, sometimes January 5th, just like the equinoxes and stuff within a year. But around January 4th. We're closest to the sun about January 4th. This point over here is called aphelion. That ap means far away, aphelion. And it happens 6 months later, so about July 4th. Okay, so we're furthest from the sun, July 4th. We're closest to the sun, January 4th. When we're close to the sun, gravity from the sun is pulling on us really hard, and it swings us really fast in a circle. So we are going fastest in our orbit here. We're going fastest right there. Let's say we're cruising this way. We go really fast. And then we slow down, slow down, slow down, slow down. So we're going the very slowest over here in our orbit. And then we speed up again, speed, speed, speed up, speed up. So we're going fastest, slower, faster, slower. And it makes a difference. And when you watch the videos in Kepler's laws, they talk about that. He actually figured out a way to see how much faster we were going by observing the planets. Yeah. Okay, so perihelion, we're closest. Now the moon, right, helio is sun. What about the moon going around the Earth? So they have the same names, but instead of perihelion, it's perigee, because like geo is Earth. So if something's orbiting the Earth, you can't say helion, you'd say perigee, and then this is apogee. So when we're far away from the moon, we're at apogee, or the moon's far away from us, it's at apogee. I guess we're far away from the moon too. When the moon is close, it's called at perigee, because the moon goes ellipse. Everything orbits an ellipse. Again, they could go in a circle, but that's not very safe. It probably would have decayed and would have spiraled in and hit whatever's orbiting now. All right, let's see. What else about ellipses do we need to know? I think that's mostly what I was going to say. Yeah, so again, you should know Kepler's laws. There's other videos you're supposed to watch on Kepler's laws. You should know enough to be able to do the ellipse project now, to fill all that out in and draw some ellipses and measure these things for yourself. But ellipses are super cool. Kepler did not want the sun, us to go around the sun ellipse. He thought everything should be circles, because circles are the perfect shape. Circles are the perfect shape. And Plato started that we should go around in circles because it's the perfect shape, and that's, you know, it seems like the heavens should be perfect. Kepler really wanted circles to work, but he found they didn't. And when he tried ellipses, they fit perfectly. And so he's had to change his mind. He didn't want to, but that's the nature of science, right? When it doesn't fit the data, you throw away circles and you go to ellipses, and that's what he did. He had to throw away his dreams of a circle because ellipses worked. So good for Kepler. I'm very proud of him for doing that. Kepler, way to go, man. All right, so thanks for listening. And now you guys are ellipse experts. Pretty cool.